On the early morning of December 3rd, 2025, something happened that no observatory on Earth had predicted. NASA's solar monitoring network, including instruments aboard the Parker Solar Probe, ESA's Solar Orbiter, and the Solar and Heliospheric Observatory, registered a sudden brief pulse originating from the precise coordinates of 3I Atlas. Not a flare, not a thermal outburst, not any known form of cometary sublimation. What they captured was something far more surgical, a 3.1 second emission, consistent in amplitude, unwavering in frequency, and embedded in a narrow spectral band that matched no known natural phenomenon. What made this emission even more remarkable wasn't just that it happened, it was how it happened. The pulse was coherent, perfect rise time, flat peak, smooth decay. Every observatory, whether in Hawaii, Chile, or deep space, logged it within a deviation of less than a millisecond. For a natural object located over 200 million kilometers from Earth, that level of timing should be impossible. Within minutes, observatories scrambled to reanalyze their logs. The Very Large Telescope in Chile, the Pan-STARRS Array in Hawaii, and even high-end amateur observatories confirmed the same structure. A momentary brightness spike with no corresponding thermal increase, no shift in rotation, and no magnetic flare. It looked, by every technical measure, like a signal. NASA's own public-facing comet tracking database suddenly stopped updating 3I Atlas data. Entries were marked as under review, and shortly after, the server began returning access errors. But by that point, multiple independent labs had already downloaded the raw data and confirmed the event, ruling out solar interference, software glitches, or internal calibration errors. The sun, during that exact window, was quiet. No CMEs, no solar flares, no elevated plasma density. This pulse came from 3I Atlas itself, and from deep within. That detail matters. Every known emission from a comet, asteroid, or interstellar object has one thing in common. It's external. Outgassing, jets, cracking ice. Surface-level explosions caused by solar heating. But this came from within the object's core, and it had no interaction with the surrounding coma, the anti-tail, or the heliospheric environment. It was contained, deliberate. Even more intriguing, when the signal was demodulated, it revealed a triple harmonic structure, with peaks at 3 Hz, 9 Hz, and 21 Hz. These ratios aren't common in natural astrophysical emissions, but they are common in engineered resonance systems, systems designed to store and release energy in timed, patterned bursts. Within hours, panic turned to silence. NASA stopped publishing live spectral logs. JWST's updated imaging feed showed a missing entry for that time window, and a leaked memo from ESA described the phenomenon as a controlled emission signature, a term reserved only for cases where an object's behavior cannot be explained by passive physics. No press conference followed, no explanation, no denial. But the signal left its mark. The instruments heard it, the timestamps matched, and the implications were simple. Something inside 3I Atlas activated, spoke for 3 seconds, then went dark again. Not by accident, not randomly, but with precision. And that's what shook the scientific community more than the signal itself. Because nature doesn't operate on microsecond timing, but technology might. Following the unexpected signal on the morning of December 3rd, scientists across multiple institutions began a full forensic analysis of the emission source. The signal's consistency had already shattered expectations, but where exactly it came from inside 3I Atlas would prove even more unsettling. Initial assumptions placed the origin at the object's surface, perhaps a jet, a sublimating vent, or some unknown reflective process on the nucleus. But high-resolution photometric overlays quickly ruled that out. There was no corresponding distortion in the coma, no localized outgassing, no tail recoil. In fact, not a single square meter of visible surface on 3I Atlas showed evidence of movement, heating, or ejection. Instead, all modelling triangulated the emission to a point approximately 70 to 110 meters beneath the outer crust, embedded deep within the solid core of the object itself. That detail alone disrupted decades of understanding about cometary behaviour. Natural emissions do not originate from inside a cometary nucleus. Heat, pressure, and solar radiation all act on the surface. But 3I Atlas, as it has repeatedly done, ignored those rules. Researchers at the Jet Propulsion Laboratory ran thermal delay simulations, calculating how heat from solar radiation could potentially trigger a delayed emission from beneath the surface. But nothing fit. There was no thermal buildup, no conductive path that could have transferred enough energy to a subsurface pocket in time to cause the pulse. The delay between peak solar exposure and signal release was too short, too sharp and too coordinated across all observatories. That's when the hypothesis shifted from thermal causation to internal activation. The leading theory now, a structure within the object, perhaps cavity-like, perhaps crystalline, acted not as a passive region but as a resonant chamber, triggered from within. This would explain the triple harmonic pattern observed in Chapter 1. It would also align with a controversial detail from earlier ESA scans, a region inside 3I Atlas that had shown non-random magnetic fluctuation even before perihelion. But what kind of natural object contains a magnetic node aligned with emission symmetry? A speculative idea emerged, a trapped core of metallic or semi-metallic material, possibly iron, nickel or silicate bound with conductive carbon, resonating under stress or internal phase shift. That might explain the reflective properties, but it still doesn't explain how such a structure would form in deep space and remain stable over interstellar distances. What makes this even more difficult to classify is that no other natural comet or asteroid has ever produced an internal origin emission that was both spectrally confined and spatially fixed. Most cometary outbursts are messy, volatile compounds exploding out in broad, unpredictable directions. But this event was neither explosive nor diffuse. It was surgically directed outward, right along the object's axis of rotation. That axis, by the way, did not shift before or after the event. That may sound minor, but it's not. A sudden energy discharge, especially from inside a rotating body, should create a torque. It should wobble the spin, destabilize its momentum, shift its orientation. But 3I Atlas didn't move, not by a single fraction of a degree. That stability implies an internal balance, either mass symmetry or active compensation. In either case, it suggests deliberate internal structure. The question then becomes unavoidable. What natural object can emit structured energy from a fixed subsurface location, with no thermal flare, no rotation change, and no surface activity? We don't have a name for that. And so, behind closed doors, some researchers have stopped calling it a comet altogether. The more neutral term being whispered now in scientific circles is interstellar structured body. Because until we understand how this object does what it just did, we can no longer pretend it behaves like a comet at all. Within hours of the mysterious signal detected on the morning of December 3rd, astronomers turned their attention to one of the most precise instruments humanity has ever built, the James Webb Space Telescope. Positioned at the second Lagrange point, L2, far from Earth's atmospheric noise, JWST had been quietly monitoring 3I Atlas for weeks. Its near-infrared spectrometer and mid-infrared imager had produced a continuous stream of high-fidelity data on the object's composition, surface texture, and thermal evolution. But on December 3rd, something changed. The expected data dump from that morning, covering the time frame between a 5:10 and 5:14 UTC, precisely when the signal occurred, was missing. The official JWST archive marked the entry as calibration hold, observational review pending. No accompanying explanation, no public update, just a gap. Normally, the JWST data pipeline is fully transparent. After initial compression and processing, observational datasets are time-stamped, assigned a processing code, and uploaded to a public server within hours, especially for objects of high scientific interest. But on this day, that didn't happen. Instead, the raw telemetry logs were pulled from the queue. Independent researchers monitoring the JWST backend quickly noticed the blackout. This wasn't a small delay. It was a manual interruption. A system-level override had reclassified the data to restricted processing, a classification used only 3 times in JWST's history, and never before for a non-terrestrial target. The implications were immediate. JWST is not an instrument that fails silently. Its detectors are cooled to near absolute zero. Its stability is legendary. And yet, when the world's most advanced space telescope turned its mirrors toward 3I Atlas, in the moments after the pulse, no data was released. Privately, several data scientists affiliated with the European Space Agency leaked portions of the calibration metadata. What they revealed was extraordinary. At the precise moment of the emission, down to the second, JWST's mid-infrared instrument saturated. The intensity spike was so brief and so narrow that it triggered an automatic filter, flagging the event as an anomaly. But it wasn't just intensity that raised alarms. One spectral channel, centered around 10.4 microns, showed a sharp, localized void, a spectral dip surrounded by otherwise normal values. Not a gap caused by data dropout, a physical absence in the photon count, a trough, as if something inside 3i Atlas had absorbed incoming radiation rather than reflecting or emitting it. This is not how comets behave. Dust and gas scatter light. They don't erase it. Multiple instruments confirmed the phenomenon. The absorption was not caused by shadow, nor by angle, nor by detector error. It was spatially confined and temporally locked to the 3.1 second pulse. It behaved like a silencing field, an engineered dampening of all outgoing radiation at specific wavelengths. This explains why JWST's data log was pulled. Not because the system failed, but because it saw something it wasn't supposed to see. Even more curiously, a private telescope array in northern Chile, operating entirely independent of NASA and ESA, captured a similar data gap in its passive infrared sweep. At the same time, across the same band. This kind of global alignment between ground and space-based systems is unheard of, unless the cause was real, measurable, and absolute. And yet no agency addressed it. Not NASA, not ESA, not the Web Science Operations Center. The media cycle passed it over. The time-stamped gap was simply ignored, erased from public discourse. But silence is data too. When the world's most powerful telescope looks directly at an object and blinks, you don't need a press release to know something's wrong. You just need to ask, what did JWST see that they won't let us see? Shortly after the December 3rd pulse from 3i Atlas was logged, scientists began examining surrounding datasets for secondary effects, anything that might help them understand the mechanics of the emission. That's when an unexpected signature appeared in the data stream from ESA's Solar and Heliospheric Observatory, SOHO, and the Canada-France-Hawaii Telescope, CFHT. It wasn't a flash, it wasn't heat, it was a Doppler echo. In normal astrophysical terms, a Doppler shift occurs when an object emitting or reflecting waves, light, sound, radio, moves relative to the observer. If it approaches, wavelengths compress and shift blueward. If it recedes, they stretch and shift redward. But 3i Atlas wasn't moving unusually. Its outbound velocity post-perihelion was already well documented. Its spin rate remained unchanged. No jets, no outbursts, no rotational acceleration. Yet, despite all this, instruments recorded a brief, clean Doppler signal returning from the object 4.2 seconds after the pulse. The first suspicion was solar interference. Could a solar flare or coronal density wave have distorted signals around 3i Atlas and created the illusion of motion? The data said no. The sun was calm. No X-class flares, no CMEs, no abnormal wind shear at that moment. And besides, this wasn't a general distortion across space. This was a tight band frequency bounce isolated to one object, returning at the exact same pitch and amplitude it had left with, shifted only in timing. Then came the second clue. The Doppler signature was symmetrical. It didn't show the typical tail-off or decay seen in natural scatterings. It arrived with a fixed wavelength, drifted by only a few millimeters per second in equivalent motion, and then stabilized. That alone shattered the idea that this was a random echo. Nature does not return clean signals, not from space dust, not from solar winds, and certainly not from cometary debris. This left researchers with an uncomfortable possibility. What they were looking at wasn't a reflected signal bouncing from a chaotic surface, it was an engineered echo. Something inside 3i Atlas had not only emitted a structured signal, but had absorbed and re-emitted a matching one. And if that's the case, then we're no longer looking at light bouncing off a rock. We're looking at resonant feedback from something with an internal structure capable of processing waves. The most conservative explanation attempted to frame this as a natural seismic rebound, a kind of shock wave or phonon echo inside the core of the object. That might occur if, say, the object had been struck by a micrometeorite, or if internal crystallization had created sudden lattice reconfiguration. but those processes leave thermal signatures: friction heat, minor flares, structural wobble. 3i Atlas showed none. Instead, what came back was coherent, almost like a sonar ping. Several labs ran synthetic modelling on the echo's profile. When played back as audio, the waveform resembled the kind of impulse response used in radar systems to identify internal structure. It had a leading edge, a sustained body, and a trailing decay. The kind of thing you hear not from a rock, but from a shell. And that's where the conversation changed. If the December 3rd signal was a transmission, the Doppler echo may have been its response, a system checking its boundary, or perhaps even interacting with solar photons as if they were part of a known equation. The final blow to the natural explanation came from Doppler phase reconstruction. When scientists overlaid the signal's entry and exit trajectories, they discovered something impossible. The shift came from the exact center of the object, not the surface, not a jet cone, not the tail. A perfect radial echo from the core, returning as if timed. This wasn't a comet reflecting noise, this was an object answering. In the aftermath of the emission event on December 3rd, a flood of observatories, government, academic and amateur, began sharing their spectral data in hopes of triangulating what had just occurred inside 3i Atlas. Most were focused on the emission burst itself, but a few researchers, particularly at the French National Centre for Scientific Research, CNRS, took a different approach. Rather than isolate the pulse, they analysed the spectral silence that followed it. What they found would send quiet ripples through the materials science community. The team, using instruments at the Pic du Midi Observatory, had been conducting high-resolution spectroscopy across mid-infrared bands for weeks leading up to December 3rd. But when they re-examined their post-pulse readings, they identified a strange anomaly, a narrow absorption trough centered at 9.26 microns that hadn't been there before. It was surgically clean, no noise, no scatter, no tapering, just a missing slice of radiation within a tight fixed frequency band. In natural objects, absorption features are messy. Water vapor leaves broad dips, silicates and carbonates create irregular valleys. But this notch, it was smooth, sharp, engineered looking, so they cross-referenced it, and that's where everything broke open. The spectral notch at 926 microns perfectly matched a known industrial material, carbon-bonded titanium silicate, an engineered ceramic compound commonly used in thermal shielding, especially in aerospace applications involving prolonged exposure to extreme radiation and high-frequency energy. This material is not found in nature, it is synthesized, and yet its spectral fingerprint now appeared embedded within an object travelling at over 200,000 km per hour through our solar system. To confirm the result, the team submitted the signature to the European Materials Database, the NASA Goddard IR Library, and even the Japanese Aerospace Agency's Composites Registry. All three returned a hit: artificial composite, high temperature resistance, reflective properties across narrow thermal bands, used in directional shielding, all engineered, all manufactured. The response from the community was immediate and cautious. Some researchers suggested it could be coincidence. Perhaps an exotic form of space-weathered mineral had developed a similar structure. Maybe it was a quirk of interstellar chemical evolution. After all, 3i Atlas originated from outside our solar system. Its elemental makeup could reflect a completely alien stellar nursery. But there's a problem with that idea. Titanium silicate requires a controlled formation process. It doesn't form in collapsing gas clouds. It doesn't bond in random cosmic dust. It requires sustained heat, pressure, and controlled cooling, conditions that only exist in designed environments. Others tried to pin the notch on external contamination, like a piece of man-made space debris embedded into the object. But the theory collapses under basic physics. Nothing from Earth or Mars or any known probe could have reached 3i Atlas's path. Its velocity, angle of entry, and isolation in interstellar space make accidental contamination statistically impossible. So the question stands, how does a naturally formed comet, composed of ice, dust, and volatile gases, suddenly present a spectral signature only found in engineered materials? One theory, quietly circulating within European astrophysical circles, is chilling. The notch wasn't there before, it only appeared after the pulse. Which means we may have just witnessed an activation event the brief ignition of an internal system that left behind a measurable residue. The pulse may not have been random. It may have reconfigured part of the object's structure or exposed a layer beneath its outer crust, a shielding composite, previously dormant. If that's true, then 3I Atlas isn't a solid rock or a chaotic ice ball. It's a layered structure, capable of hiding its internal composition until a specific trigger is met. And now that it's exposed, we're beginning to see the edges of something far more complex and far less natural than a comet. As data from the December 3rd emission settled into observatory archives, one set of numbers refused to align with expectations: temperature. From the James Webb Space Telescope, the Solar Orbiter, and multiple ground-based infrared telescopes, thermal readings of 3I Atlas were clear, consistent, and in direct contradiction to every known law of passive heat exchange. The object had pulsed. That much was now undeniable. It had released a short, structured emission visible across several wavelengths. But when researchers examined the thermal footprint of that pulse, they discovered something that should be physically impossible. There was no heating. In fact, the data suggested a slight drop in temperature during the brightest phase of the pulse. According to the JWST's near-infrared spectrometer, the face of the object directed toward the sun, the side that should have received the highest energy exposure, cooled by nearly 6 degrees Kelvin during the 3.1 second signal. That isn't how comets behave. That's not how anything behaves. In normal cometary physics, solar radiation heats surface materials. Ice sublimates, gas escapes, dust erupts, and energy radiates outward in chaotic waves. But 3I Atlas didn't flare, didn't boil, and didn't react thermally. Instead, it appeared to stabilize, even regulate, its internal temperature during the event. This forced scientists to ask a different kind of question. What if the object isn't just non-compliant with thermal expectations? What if it's actively controlling how it interacts with heat? At the University of Oslo's Magnetoplasma Lab, researchers began comparing the thermal behavior of 3I Atlas to advanced terrestrial systems, particularly phase-change metamaterials and photonic crystals engineered to manipulate electromagnetic radiation. These materials can be designed to reflect, absorb, or redirect heat at selected frequencies. They don't radiate like typical solids. They choose which energy to release and when. One theory proposed that the surface of 3I Atlas may not be uniform. Instead, it could be composed of layered thermal filters, similar to passive radiative cooling structures used on Earth's satellites, which can shed infrared heat while maintaining surface stability. But the comparison didn't end there. The spectral heat signature of 3I Atlas, when viewed across multiple bands, revealed something far more disturbing. The object's coldest zones were also its brightest. Regions that emitted the most visible and ultraviolet light were simultaneously losing less heat. In other words, the object was emitting energy without heating up. This contradicts Stefan Boltzmann's law, the foundational principle that governs the radiative heat of bodies in space. It says that the hotter something gets, the more it glows. But 3I Atlas was glowing, while getting colder. The only plausible explanation? Active thermal decoupling. In engineered systems, this is achieved through internal thermal routing, directing excess energy along specific paths to avoid overheating. It's a principle used in the design of spacecraft, satellites, even high-end computing chips. But to see a similar behavior in a supposed interstellar rock is not just unexpected, it's unclassifiable. And then came the final twist. Measurements from ESA's solar orbiter showed localized electromagnetic field distortions around 3I Atlas during the emission. These were weak but measurable, suggesting that the object wasn't just passively reacting to solar input. It was producing a field, a controlled shell that may have acted as a kind of heat buffer or radiation lens. If true, this would mean 3I Atlas is not simply surviving its journey through the inner solar system. It's managing its energy environment, adapting in real time, and staying structurally stable through processes we do not yet understand. And if an object can control its heat, its emissions, and its exposure, then the next question is no longer what is it made of, it's who or what designed it to work this way. As the implications of the December 3rd emission continued to unfold, a separate anomaly began to surface. This one not in the skies, but on Earth itself. Within minutes of the pulse from 3I Atlas, 2 magnetometer arrays, one located in Kiruna, Sweden, and the other near Fairbanks, Alaska, recorded synchronized magnetic disturbances. These were not large-scale geomagnetic storms or residual noise from solar-wind interactions. They were sharp, localized deviations, each lasting approximately 1.3 seconds, and each occurring exactly 499.2 seconds after the 3i Atlas signal, the precise time it would take for an electromagnetic wave to travel from the object's location to Earth. At first, the anomaly was dismissed. Earth's magnetic field is constantly in flux, shaped by solar wind, cosmic radiation, and the subtle shifts of Earth's own ionosphere. But then another observatory, the Canadian Geospace Observatory in Saskatchewan, reported the exact same signal, same strength, same delay, same timestamp. That's when researchers realized this wasn't a fluke. It was a coordinated magnetic echo, arriving globally, on schedule, and originating from one known source. And that source was 3i Atlas. This forced scientists into uncomfortable territory. No known comet, asteroid, or interstellar object has ever been associated with Earth-based magnetic interaction, let alone one that exhibits coordinated timing and repeatable structure. Even during intense solar storms, Earth's geomagnetic field tends to react in chaotic ways. But this wasn't chaotic, it was geometrically clean. So what caused it? To find out, researchers ran the event through a system normally reserved for analysing solar flare effects. They mapped the propagation vector of the magnetic wave, triangulated it against Earth's position, and plotted the angular convergence. What they found was startling. The magnetic pulse had not simply radiated outward into the solar system. It had targeted a narrow field cone, one that just happened to intersect Earth's magnetosphere at that exact moment. This wasn't just magnetic emission, it was magnetic directionality. If the object had been a spacecraft, this would look like a focused scan, a brief, low-power electromagnetic sweep tuned to measure planetary magnetic resistance or atmosphere density. But of course, that would imply intent. So researchers looked for natural explanations. They found none. No solar activity aligned with the spike, no nearby planetary interactions, no background field anomaly. The only remaining candidate was the object itself. And then came the final piece. The magnetic signature embedded in the pulse mirrored the frequency structure of the original emission, 3, 9, and 21 Hz components, layered and harmonically spaced. The exact same ratio previously detected in the light pulse. But this time, those frequencies were encoded into magnetic flux, not photonic energy. This was not just a multi-wavelength event, it was a multi-domain event, optical, thermal, and now magnetic. More alarmingly, simulations showed that Earth's magnetic field did more than just receive the pulse, it briefly resonated with it. Magnetometers across the northern hemisphere detected a faint after-echo, a kind of electromagnetic ringing, as though the planet itself had vibrated in response. Not strong enough to trigger any physical effects, but too structured to be ignored. This led to a theory many refused to entertain, that the object had not simply emitted a signal. It had measured something in return. The emission went out. Earth's field responded, and 3i Atlas, still outbound, had been in the right position to receive the echo, to detect our planet's magnetic fingerprint mapped in perfect detail. If that's true, then the pulse may not have been about communication. It may have been a scan. And if an object from interstellar space can scan Earth's magnetic field with precision, then somewhere inside 3i Atlas, there is more than ice and dust. There is a system, there is feedback, and now it knows we're here. While most eyes were on the immediate aftermath of 3i Atlas's December 3rd pulse, analysing emissions, magnetic returns, and Doppler echoes, one group of scientists quietly turned their attention to what didn't happen, or more precisely to what couldn't be seen. That group was part of the James Webb Space Telescope's near-infrared camera, NIRCam science team, conducting routine background surveillance when they noticed something strange, a blank corridor in the data, an area around the object that appeared to absorb or cancel incoming signal. They called it the silent zone. At first, they assumed it was a software issue, a calibration glitch, lens flare, or interference from background stars. But the anomaly persisted across multiple filters and time points. Wherever 3i Atlas moved, a narrow halo trailed just behind it, approximately 11 arcseconds wide, registering significantly lower reflectivity than the surrounding space. In astrophysical terms, this is unprecedented. The vacuum of space doesn't mute light unless something is physically absorbing it. And even then, absorption usually comes with a trade-off: dust trails, thermal bloom, or reflected emissions. But in the case of this silent zone, there was nothing. No re-emission, no trailing debris, no flare halo, just an area where data disappeared. When processed through JWST's false color infrared rendering, the zone showed up not as black, but as perfect grey, equalized, leveled, erased, as though whatever occupied that zone had neutralized signal variance entirely. This led to an unsettling hypothesis. The silent zone wasn't an absence of material, it was an active field. An instrumented spacecraft can generate such zones using field cancellation, a concept seen in advanced stealth aircraft on Earth. These systems use magnetic or electric field manipulation to reduce signal bounce, making the object harder to detect. But the technology to do this in open space, at interstellar speeds, and without a power source visible in any spectrum, and that technology is, by our standards, not just advanced, it's unreal. More troubling, the shape of the zone didn't fluctuate. It held a fixed radius regardless of distance to the Sun, and even adjusted its angle in sync with Earth-based observations. In short, the zone was aware of its observers. Teams at NASA Goddard cross-referenced this data with earlier JWST scans, looking for signs that the silent zone might be a camera artifact. What they discovered was even more unsettling. The zone wasn't present in October or November. It appeared just 3 days before the pulse event and intensified after it. This confirmed what many suspected. The zone was not natural, it had been activated. But why would an object hide part of itself? One theory is internal shielding. If 3i Atlas contains delicate systems, or some kind of computational core, the silent zone could act as a protective shell, a way to mask heat signatures or structural reflections from high-powered telescopes like JWST. Another theory, more controversial, is that the zone might function as a directional communication shroud, blocking unintended emissions while a specific vector transmits data. But the strangest feature came not from what the JWST saw, but from what it didn't. Using pattern recognition software designed to reconstruct partially occluded objects, analysts attempted to fill in the silent zone using surrounding light. Normally, this process estimates surface features based on symmetry and brightness gradients. In this case, the result was impossible. The reconstructed shape revealed a perfect octagonal form, centered within the masked region. Comets do not contain symmetrical, solid internal structures, let alone geometry. And yet, for several frames, JWST imaged exact radial lines extending from the object's center, as if some inner structure was briefly catching starlight, before vanishing again. If this was a glitch, it was the most symmetrical glitch in JWST's history. If it wasn't, then inside 3i Atlas we may be staring at a structure, not just shielded by dust or plasma, but cloaked by intent. And now even the most advanced space telescope ever built can't see what's inside. Following the pulse event of December 3rd, astrophysicists began reanalyzing the emission profile of 3i Atlas across all available datasets: photometric, spectroscopic, and radiometric. But one dataset in particular, collected from a chain of radio telescopes across Finland, South Korea, and Chile, revealed something no one had expected to find: a repeating harmonic wave structure embedded within the initial burst. To be clear, comets do not emit structured signals. Their interactions with solar wind, cosmic radiation, and interstellar dust are chaotic and broadband. Even when they emit radio waves, the patterns are erratic, caused by charged particle collisions or sublimation noise. But 3i Atlas was different. The waveform captured by the Atacama Large Millimeter Array, ALMA, in Chile showed 3 nested frequency peaks at 3.0 Hz, 9.1 Hz, and 21.3 Hz. These weren't just random spikes. They were mathematically proportional, forming a classic harmonic ladder. In audio engineering or quantum physics, such spacing implies either resonance or intentional encoding. Immediately, the signal was sent to spectral analysts specializing in astrophysical harmonics. Their conclusion: the waveform didn't originate from random physical reactions. It had resonant fidelity. That is, it preserved phase alignment over time, which only happens when energy is released through structured oscillators. On Earth, This kind of profile is found in everything from musical instruments to tuned lasers. In the natural world, it's almost exclusively seen in atomic transitions, not in kilometre-scale objects drifting through the solar system. Even more bizarre was the wave's decay profile. Instead of trailing off chaotically, the harmonic components of the pulse ramped up, peaked in a fixed ratio, and then cut off cleanly, as if someone had toggled a switch. The total event duration was 3.1 seconds, yet each harmonic sequence fit exactly within 1-second intervals, suggesting a modular transmission sequence. One possible explanation, presented by Dr. Anna Valek at the Institute for Radio Astronomy in Trieste, is that 3i Atlas may contain internal cavities or structured resonators. These would act like chambers in a wind instrument, amplifying and refining energy as it exits. But to achieve this effect at such a clean signal-to-noise ratio, those chambers would need to be precise, sub-millimetre accuracy over long distances. That is beyond anything known to occur naturally in cometary formation. Another theory suggested that the wave structure wasn't just a byproduct of internal mechanics, but an intentional emission, a test pattern, diagnostic pulse, or an encoded data burst. In fact, encryption researchers in Germany's Fraunhofer Institute attempted to overlay modulation templates on the waveform and found partial matches for quadrature amplitude modulation, QAM schemes, used on Earth to transmit digital information. Though speculative, this raised a terrifying possibility. What if the pulse wasn't just harmonic? What if it was data? In this scenario, the three frequencies would serve as carriers, with embedded shifts in amplitude and phase encoding actual content, and the clean cutoff. That could indicate packet boundaries, suggesting that what we saw wasn't a flare or emission, but the first completed transmission from inside the object. Support for this idea grew when Japan's Kagoshima Space Observatory noted a secondary echo wave 14 seconds after the primary pulse, bearing the same harmonic ratios but slightly shifted as if correcting for environmental interference. Natural bodies don't rebroadcast at adjusted frequencies. Artificial systems do. Still, not everyone agrees. Skeptics argue that interstellar noise or overlapping radiation sources could mimic harmonic structure under the right conditions. They caution against interpreting patterns as intention. But even those voices admit, this one's different. Because even after accounting for noise, the pattern persists, and wherever 3i Atlas moves next, radio dishes around the world are now locked onto it, not for its brightness, but for its rhythm. The universe may be full of soundless rocks, but this one is humming. By December 3rd, most observational arrays tracking 3i Atlas had already catalogued an extensive range of unusual behaviours, its asymmetric motion, its harmonic emissions, and its cloaked silent zone. But one of the most quietly disturbing anomalies went almost unnoticed at first. It was the tail, or rather, what the tail wasn't doing. In a normal comet, the tail, made of gas, dust, and ionized particles, reacts instantly and visibly to solar radiation. When the sun heats the comet's surface, volatiles sublimate and shoot outward, creating long glowing trails that flare, twist, and shift depending on the solar wind's pressure and direction. But 3i Atlas showed none of these behaviours. In fact, it seemed to reject them altogether. As the object approached a zone of increased solar flux, passing near one of the denser magnetic filaments stretching between the Sun and Mercury, astronomers expected to see turbulence in its plasma trail, a flare, a spike, a ripple, something. What they saw was nothing. The tail of 3i Atlas remained completely linear, unshaken, unresponsive. Even as a coronal mass ejection, CME, passed within a few degrees of its orbital plane, the tail held its shape, length, and vector. That's never happened before, not even with Oumuamua. Telescopes in Hawaii, New Mexico, and Tenerife captured high-resolution time-lapse sequences of the tail across ultraviolet and visible spectra. Not only did the tail fail to shift direction, but it also lacked the ion striations that naturally occur when solar particles interact with cometary gases. In normal ion tails, you see fragmentation, you see dance, you see motion. But this tail looked frozen, almost like a solid light structure, unaffected by external forces. Some speculated that the material being ejected was denser than average. Others thought the object might be too far from the Sun to react as expected. But both theories collapsed when new measurements confirmed that the object's surface temperature was well within the range to sublimate common volatiles. Carbon dioxide, methane, ammonia, all should have been active. The coma surrounding the object also told a confusing story. Rather than blooming outward in a wide spherical halo, it appeared to be tightly constrained, forming a narrow cone no more than 800 kilometers in width, unusual for an object estimated to be over 300 meters across. It was as if the gas was being funneled, or worse, contained. And then came the strangest discovery of all. Spectral analysis showed a total absence of expected molecular signatures. No CN, no C2, no OH lines, gases typically visible in every known comet's outgassing process. Instead, the tail emitted a narrowband glow centered around 580 nanometers, a wavelength more closely associated with engineered sodium vapor systems than any natural cometary process. That prompted a chilling question. Is it a tail at all? If 3I Atlas isn't venting gas, and the supposed tail doesn't react to solar pressure, then what are we looking at? Some now believe the structure may be an energy trail, not material ejection, a residual ion sheath resulting from field interaction or controlled particle release. Others argue it could be a propulsion exhaust, stabilized to avoid turbulence, masked to mimic cometary behavior, but failing to replicate natural reactions under solar stress. Still others think it's simply a byproduct of whatever system lies beneath 3I Atlas's outer shell, a side effect of internal energy redistribution leaking into space. But no matter the theory, one fact remains. The tail of 3I Atlas doesn't move, it doesn't shift, and it doesn't scatter, even when the solar system tries to push it. In the world of natural comets, that's not just rare, that's impossible, and if it's not natural, then something is holding it in place, on purpose. For days following the December 3rd pulse from 3I Atlas, analysts across multiple observatories remained focused on what the object was doing, emitting signals, deflecting solar interaction, and cloaking parts of itself from view. But the most unexpected data point came not from what it did, but from when it did it. The anomaly was a delay, and not just a minor lag, but a precisely measurable 12.9-minute offset between two sets of observed phenomena. The pulse's optical burst and the corresponding gravitational lensing signature. Here's why that matters. When an object of substantial mass emits a strong electromagnetic burst, especially one observed in multiple wavelengths like the December 3rd event, both the light and the gravitational influence from that event should arrive at the same time. Gravitational effects propagate at the speed of light. It's a bedrock principle of general relativity. But as astronomers from the Virgo Interferometer in Italy and LIGO in the United States scanned data from their respective gravitational wave detectors, they noticed something subtle, a low-amplitude, localized lensing distortion consistent with a sudden shift in the mass-energy distribution of the region near 3I Atlas. It wasn't a full gravitational wave. It was more like a microdip in spacetime curvature, a ripple indicating a sudden contained mass redistribution, as if something inside the object had shifted or restructured itself. This wasn't entirely unexpected. A rapidly spinning or discharging object might momentarily disrupt the gravitational field around it. But the problem was timing. The optical signal, the visible and infrared pulse from the object, arrived 12 minutes earlier than the gravitational lensing effect. That shouldn't be possible. If the event were natural and simultaneous, both signals would reach Earth observers at the same time. The only way to explain the delay is if the two events were not simultaneous at all. But if that's the case, the implication is staggering. Either the light pulse preceded the mass shift by 12.9 minutes, or something along the path of the gravitational distortion interfered with or delayed its arrival. This led to two possibilities, both equally extraordinary. Scenario 1. The pulse was intentionally released before a known mass reconfiguration inside the object. That would suggest internal systems with advanced timing control, allowing the object to predict and sequence its emissions. This would move 3I Atlas even further away from being a passive natural object, and closer to something coordinated. Scenario 2. The gravitational lensing signal took a longer path through curved spacetime, possibly diverted or delayed by an unknown intermediary structure between 3I Atlas and Earth. That would imply the presence of a gravitational field-altering medium somewhere along the line of sight. Researchers briefly explored the idea of a dark matter cloud, but simulations didn't support such a concentrated distortion. Others considered whether a cloaking system inside the object might temporarily shield gravitational influence, delaying the spacetime response. That technology is far beyond human capability, but if real, it would mark the first time in history such a mechanism has ever been detected. The more conservative analysts proposed a third theory, that our interpretation of the event timing might be flawed. Perhaps the timestamps from JWST and ground-based interferometers were not perfectly synchronized. But a thorough audit showed that all instruments were accurately synced within milliseconds. The delay was real. 12 minutes. 12 minutes between light and gravity. And within that gap, we're left with a chilling question. Why? Why would any object delay its gravitational footprint? Why would a signal arrive before the mass that caused it? Unless the light was a warning, and the mass shift wasn't a side effect, it was activation. If there's one certainty in cometary observation, it's this. When something changes, especially violently, something breaks off. Whether it's a fragmenting nucleus, a burst of gas, or a high-speed flare triggered by solar stress, there's always a residue, a trail of particles, fragments, or dust clouds left in its wake. But 3i Atlas didn't follow the rules. In the early hours of December 3rd, following the pulse event, dozens of high-resolution telescopes were fixed on the object's trajectory, prepared to document whatever physical effects might unfold. Astronomers expected at minimum a burst of ejecta, or even a slow fragmentation event, a common fate for icy bodies under intense thermal and gravitational strain. Instead, they saw something entirely different. Nothing. There was no fragmentation, no brightening flare, no widening of the coma, and most baffling of all, no dust. Initial reports from ESA's Optical Ground Station in Tenerife and NASA's Infrared Telescope Facility, IRTF, in Hawaii, confirmed a consistent surface profile before and after the pulse. The object's magnitude remained steady. Spectral scans detected no increase in common sublimation, byproducts such as CN, C2 or OH, molecules that usually spike during energetic cometary events. To put it plainly, 3i Atlas pulsed, and then it held. This created a problem. If no material was ejected, then where did the energy of the pulse go? Observers described the burst as being similar in scale to a micronova in terms of optical brightness. Yet unlike a nova, there was no outward force, no blast wave, and no particulate bloom. Several teams ran simulations to try and model a comet maintaining cohesion after such an event. None succeeded. The mathematics refused to cooperate. The structural stress alone, given the observed energy, should have torn the object apart. But the structure held. Not a single shard was visible in the surrounding orbital corridor. This wasn't just abnormal, it was unprecedented. At this point, new hypotheses emerged. Some suggested that the object was protected by an internal compression field, absorbing the recoil. Others floated the possibility that the pulse didn't come from the outer layer at all, but from within, as if it had originated in a shielded core, with the outer layers merely acting as a filter. Another possibility. The pulse wasn't a mechanical event, but a type of energy release not associated with heat or force. Something more like a data discharge or signal emission, causing light without physical impact. But then came an even stranger observation. Astronomers from the Swedish 1M solar telescope noticed that after the event, the object's albedo, its reflectivity, slightly increased. Not enough to suggest ice shedding or surface cleaning, but enough to imply that whatever was coating the surface had changed. One theory posits that 3i Atlas is covered in an adaptive material, perhaps a layered structure capable of reorienting or reforming after each event. Think of a smart skin, responding to stimuli with microscopic adjustments, perhaps even shedding a single molecular layer that's invisible to standard instruments. But if that were the case, we'd still expect some trace signature, a dust bloom, a thermal shift, a chemical trail. And yet, nothing. The post-event silence was total. This lack of debris is now considered one of the strongest pieces of circumstantial evidence that 3i Atlas may not be a comet at all. Natural. Bodies, even the most resilient, fracture and shed. They scar. They leave behind trails of destruction. But this object moves with surgical control, precision, and containment. No fragments, no flare, no dust. And if there's no debris, there's only one place the energy could have gone. Back inside, which raises the question, what kind of object pulses light outward and then seals itself shut, without a trace? It didn't make the headlines. There was no press release, no formal public statement, no coordinated announcement across space agencies, but it happened. At 4:42 UTC on the morning of December 3rd, just under 6 hours after 3I Atlas emitted its mysterious optical pulse, multiple observatories were quietly instructed to cease open transmission of live data pertaining to the object's trajectory, photometric readings, and radio signal captures. What followed is now referred to within the astronomy community as the Lockdown Directive. This term didn't originate from government documentation. It was coined by researchers in forums and encrypted messaging groups who noticed a synchronized pattern: sudden data gaps, live feed interruptions, and unexplained maintenance notices appearing on the pages of otherwise transparent sky monitoring platforms. The first major blackout came from the Solar Dynamics Observatory, which had previously been streaming near real-time magnetogram overlays of the region surrounding 3I Atlas. At precisely 4:44 UTC, the stream was paused for calibration. Then came ESA's Solar and Heliospheric Observatory, SOHO, which removed its LASCO C3 image stream for exactly 72 minutes. The time window matched precisely the moment when 3I Atlas would have been fully visible, passing through the camera's radial field. Next was NOAA's Dieskova satellite, which despite being fully operational failed to update its solar wind telemetry data for over 2 hours. No explanation, no error logs. What was happening wasn't technical, it was procedural. Insiders began to whisper. Employees at a Chilean observatory posted anonymized messages noting that their tracking directives had suddenly changed. One operator reported being told, all optical data from quadrant 42C is to be logged but not publicly mirrored. At the same time, amateur astronomers across Australia and Taiwan began reporting strangely delayed ephemeris updates, as if the predicted path of 3I Atlas was being reissued with offsets that didn't match the object's real-time sky position. But the clearest sign came not from missing data, but from policy revision. On December 3rd at 10:17 UTC, the European Southern Observatory, ESO, temporarily suspended open access requests for 3I Atlas-related observations. The form that had previously allowed researchers to request historical photometric scans now returned a message: dataset under review for calibration accuracy. This phrase, calibration accuracy, has since become a euphemism within the science community for classified review. Why would space agencies, tasked with transparency and data sharing, initiate such a coordinated blackout? And why now, after months of open tracking? The prevailing theory is simple. They saw something, and whatever it was, it required time, silence, and most of all, containment. Because once multiple independent instruments had confirmed that the pulse from 3I Atlas did not behave like a natural event, a new layer of protocol likely activated, a contingency protocol designed not for comets, but for non-natural anomalies. It's been speculated that buried deep within the operational playbooks of agencies like NASA, ESA, and CNSA are non-disclosure triggers, events that, if confirmed, initiate Type 2 data lockdown procedures, removing civilian access to avoid panic, misinterpretation, or premature exposure of unknown phenomena. This isn't just conjecture. Declassified documents from earlier decades reveal similar patterns during Cold War satellite anomalies and deep space radar returns that defied classification. In each case, data was delayed, rerouted, or quietly erased. Now, it appears 3I Atlas has triggered a similar response. No sirens were sounded, no astronauts called home. Just a silent wave of permissions revoked, windows closed, and data rerouted. Because something inside that object blinked, and the world's most powerful agencies blinked back. What happens when space doesn't behave the way we expect? Apparently, they shut it down. When 3I Atlas emitted its now infamous optical pulse in the early hours of December 3rd, the scientific world didn't immediately grasp the significance. After all, objects in space flare all the time, whether due to solar reflection, gas ignition, or impact events. But this flare was different, not in brightness, not in duration, but in its signature. The energy profile of the pulse was unnatural. Across infrared, ultraviolet and visible spectrums, the signal carried a structure, a repeatable waveform with discrete harmonic intervals that should not exist in a spontaneous thermal event. Normally, when a comet reflects sunlight or vents internal pressure, the emission appears as a chaotic blend of wavelengths, uneven, scattered, thermally broad. But what 3I Atlas produced was coherent, almost like a broadcast. Scientists from the Atacama Large Millimeter Array, ALMA, and NASA's Deep Space Network converged on the raw data and independently confirmed a chilling pattern. The pulse carried energy peaks at evenly spaced frequencies, centered on 1420 MHz, 2840 MHz, and 4260 MHz. These are not random numbers. The 1420 MHz line is known globally as the hydrogen line, a natural emission frequency used by astronomers for deep space radio observation. But it's also the standard reference point used in interstellar signal searches, including by SETI. The idea is simple. If an intelligent civilization wanted to announce itself using universal constants, this is the frequency they would choose. But 3I Atlas didn't just emit on 1420, it emitted on harmonics of it, precise multiples that suggest intentional modulation, not thermal chaos. That's not comet behavior, that's engineering. This prompted rapid escalation in interest from communications theorists, SETI analysts, and even cryptographic specialists, who began to pass the pulse for potential encoded structure. Early analysis hinted at modulated amplitude, possibly encoding binary data. But before full decoding efforts could begin, agencies pulled back. Several high-energy observatories were issued advisory memos to suspend speculative interpretation of anomalous harmonics pending further classification. Translation: stop analysing it, or risk crossing an invisible line. What remained available to the public came mostly from amateur radio astronomers, many of whom had been recording the sky independently and without restrictions. They confirmed the signal's repeatable structure, noting that the harmonics were precisely timed to match the object's transit vector across the solar magnetic field. In other words, the object seemed to know where it was, and its pulse matched the environment around it, as if adapting its emissions to interface with the heliosphere itself. But that wasn't even the strangest part. Spectroscopic breakdown of the emission revealed a narrowband spike near 589.3 nanometers, a spectral line corresponding to sodium vapor, commonly found in low-pressure artificial light sources on Earth. This line should not appear in a cold, dust-covered object from outside the solar system, and yet it did. Exactly at the peak of the pulse, this raises uncomfortable possibilities. Sodium emission in this narrow band, when modulated alongside radio harmonics, points to dual-channel communication, light and radio, synchronized, perhaps to be readable by very different receivers, a technological design, not a natural occurrence. Why does the energy signature matter? Because it carries intention. If you throw a rock into space, it reflects sunlight. If something pulses light across multiple bands, on specific frequencies, with precision timing, that's not a rock, that's a signal. And if 3I Atlas is signaling, either outward, inward, or directly toward Earth, then we are no longer dealing with a celestial object. We're dealing with a message, one that some agencies have already tried to stop us from hearing, and one that may have been waiting to be detected at exactly this point in its orbit. In standard cometary physics, tails behave predictably. A comet develops two distinct outflows, a dust tail that curves along its orbital path, and an ion tail that streams directly away from the Sun, pushed by solar wind and electromagnetic pressure. But in rare cases, a third phenomenon appears, the anti-tail, an illusion caused by Earth's viewing angle and orbital geometry, making the dust appear to stream toward the Sun. But 3I Atlas did more than just form an anti-tail, it inverted it. This strange event was observed in the hours following the pulse on December 3rd, when solar observatories and backyard astronomers alike began to notice an unsettling visual shift. Instead of following the expected trajectory, arched backward from its orbital momentum, the anti-tail of 3I Atlas folded in toward the body, paused, and then reoriented downward, toward a point beneath the object, as if magnetically locked to something not in space but in geometry. Initial theories suggested a change in solar wind velocity. However, data from the solar orbiter confirmed no CME, flare, or solar stream change during the time of observation. The Sun's output had been unusually calm, a quiet heliophysical period that should have preserved a stable tail configuration, and yet the tail moved. Not gradually, but in a matter of minutes. The inversion wasn't just visual. Spectrographic data collected during the reorientation showed a sudden red shift in the tail's molecular emissions. This red shift was not due to classic Doppler recession, but to compression of emitted light, as if the ions were being drawn inward rather than expelled. It's the opposite of what you'd expect from a comet under pressure. It was imploding. Several physicists from the International Heliophysics Conference called it the most confusing signature they had ever seen, a contracting anti-tail, displaying a persistent red shift, but without any acceleration or mass ejection. It was as if space itself around the object was bending, allowing light to escape on paths not consistent with the object's motion. One hypothesis emerged that caused a wave of internal controversy: gravitational lensing from inside the object. This idea is virtually unprecedented. Lensing usually occurs when a massive object bends light from a more distant source. But in this case, the light was coming from 3i Atlas itself, suggesting that either it was emitting from multiple layers within, or it was passing through an internal structure dense enough to warp its path. If 3i Atlas contains a hollow gravitational core, or some form of localized space-time distortion, it could explain the tail's inversion. It could also explain why the emissions arriving from the tail were redshifted, not from speed, but from energy loss as photons crossed a curved field. Even more intriguing was what followed. High-speed imaging revealed oscillations in the tail, pulses of contraction and release, timed to precisely 9.3-minute intervals. The periodicity was too clean for turbulence. It resembled modulated gravitational feedback, or even a controlled reaction occurring inside the object. Some researchers quietly dubbed this phenomenon the inversion engine, suggesting that the tail's movement wasn't passive at all, but part of an active field manipulation system designed to interact with solar particles or electromagnetic layers in the heliosphere. The implications are immense: a tail that bends, retracts, and redshifts on command, a structure that appears to warp light from within, a comet that doesn't just react to space, but reconfigures it. And all of it started when the object pulsed. So now we ask, is this an atmospheric anomaly? Or are we witnessing the maneuvering of something designed to hide itself, not just from human eyes, but from the very physics we use to look, because a red-shifted anti-tail, that folds inward instead of away, means the energy isn't escaping, it's being stored. In the hours following the pulse, emitted by 3i Atlas on the morning of December 3rd, astronomers prepared for the most basic and predictable consequence: a brightness spike. In normal celestial terms, when a cometary body expels energy, whether from solar heating, internal pressure, or physical disintegration, its visible magnitude increases. That's because it usually sheds ice, dust, or gas, creating a larger coma and a more reflective surface area. But with 3i Atlas, the opposite happened. It didn't brighten at all. For nearly every active body we've tracked entering the inner solar system, the pattern is clear: get closer to the sun, get hotter, eject more material, and become brighter. Some comets double or triple in brightness in just a few hours following internal events. This is not just a guideline, it's a law of observational astrophysics tied to mass, radiation, and surface chemistry. Yet when researchers from the Pan-STARRS Observatory and the IRTF in Hawaii compared pre- and post-pulse photometric data, the object's apparent magnitude remained within 0.02 deviation. That's within noise margin. No significant brightening occurred, no increase in surface reflectivity, no coma expansion, no radiative bloom. This non-event was so shocking that many teams suspected instrument error. Datasets were double-checked, filters recalibrated, and ground-based telescopes used as independent verification. The results were identical. The object had pulsed, but its luminosity remained static. Some tried to explain it away as a directionality issue, that perhaps the pulse only radiated in one vector, away from our observational line of sight. But then came another layer of confusion. Spectral energy output across all wavelengths also remained flat. From ultraviolet to infrared, there was no evidence of enhanced thermal emission. If this wasn't a flash of heat or gas, then what was it? The answer may lie in non-luminous energy, a type of event that releases power not through light, but through structured fields or invisible emissions. In this model, the pulse we captured wasn't reflected sunlight or burned off matter, but a carefully engineered discharge, meant to be seen, but not meant to change the object's state. And that's what unsettled astronomers the most. In traditional astrophysical systems, energy and brightness are inextricably linked. More energy, more photons, more brightness. But 3i Atlas somehow broke that relationship. It discharged something powerful enough to register on multiple instruments, including radio, optical, and magnetospheric sensors, but left no thermal residue. That implies the pulse was either non-thermal, suggesting exotic radiation, or database signaling internally absorbed, meaning the energy was recycled within the object. Not from the object's surface at all, but from a contained internal source. Another red flag came from the Spitzer-derived heat maps, which showed that post-pulse infrared values actually slightly decreased in some bands. This could suggest that the object was cooling, not heating, a reversal of the usual thermodynamic trend after energetic events. This has led to one of the more radical hypotheses, that 3i Atlas has adaptive shielding. In other words, a material or structure that compensates for energy discharges by instantaneously redirecting or reabsorbing surface heat, thus maintaining a consistent observational signature, even after dramatic internal shifts. This behavior is common in engineered systems, especially those designed to cloak or regulate emission profiles for stealth or energy conservation. But for a comet, it's unheard of. The lack of brightening, when combined with the previously documented spectral anomalies, points toward total emission control. It's as if the object wants to be seen, just enough, but never fully understood. A visible silhouette, but with all the revealing physics stripped away. Because if something can emit a powerful pulse, without getting brighter, without shedding mass, and without heating up, then we're no longer observing a natural process. We're observing a performance, one calibrated to our instruments, and possibly for our eyes. At 9:46 UTC on the morning of December 3rd, just hours after the unexplained pulse emitted from 3i Atlas, a quietly updated entry appeared in the internal tracking database used by several European astronomical institutions. It was a metadata tag, small, non-public, and devoid of fanfare. But it changed everything. The European Space Agency, ESA, had reclassified the object. Prior to this moment, 3i Atlas had been listed under the traditional coding of I for interstellar object, consistent with its hyperbolic trajectory and observed path from beyond the solar system. But this classification was appended. A second code was added, ANEO observation priority. This means asteroidal object, near-Earth object tracking status, elevated. This seemingly simple adjustment carried enormous implications. First, it signalled a shift in ESA's internal framing of 3i Atlas. No longer just a comet from interstellar space, but now categorised as a near-Earth object requiring orbital vigilance, something typically reserved for bodies with even the slightest potential to enter Earth's orbital corridor. But the reclassification didn't stop there. A second internal memo was issued through the Near-Earth Object Coordination Centre, NEOCC, located in Frascati, Italy. This memo, flagged for Level 2 scientific clearance, was quietly leaked through an independent data analyst based in Hamburg. The memo's subject line was titled Trajectory Review Request, 3i Object, Phase-Locked Rotational Pattern. This phrase, phase-locked rotational pattern, set off alarms within the scientific community. It implies that 3i Atlas's orientation is not tumbling randomly as expected of natural comets, but is instead synchronized in a stable configuration, likely aligned to solar or magnetic coordinates. That kind of behavior isn't accidental. It's consistent with artificial satellites, probes, or controlled bodies. Any object maintaining a fixed rotational alignment for energy harvesting, communication, or propulsion efficiency. The memo went on to cite anomalous consistency in the object's albedo reflection pattern, meaning it was reflecting sunlight from fixed surface points over time, without the random rotation seen in most natural bodies. This could only occur if the object had intentional axis control, another red flag. Now, reclassifications happen all the time. When an asteroid turns out to be a binary system, or a comet unexpectedly fragments, agencies adjust their tags. But what made this different was the lack of any public announcement. There was no bulletin, no press release, no update to ESA's online dashboards. Why hide it? The most likely explanation is that this reclassification triggered international protocols tied to high-risk or ambiguous objects, especially those exhibiting characteristics that don't fall within traditional astrophysical models. Once an object is classified under certain threat tiers or intelligence flags, it may enter a zone of restricted scientific access, and that appears to be exactly what happened. In the days following December 3rd, several researchers across Europe reported failed requests to access high-resolution data archives from the Very Large Telescope, VLT, CHEOPS, and Gaia. The denials were attributed to observation prioritization shifts, a vague phrase typically used when an object has been internally escalated beyond standard access levels. Even more curious, the European Space Operations Centre, ESOC, responsible for space safety and coordination, posted a transient advisory on their internal portal, flagging anomalous rotational telemetry on an unnamed object, again widely assumed to be 3I Atlas. Put together, these quiet administrative moves point to a single uncomfortable conclusion. ESA may now consider 3I Atlas to be non-natural, or at the very least an object whose behaviour warrants restricted classification, because when an interstellar visitor changes classification to a near-Earth monitored body, when its spin locks to solar coordinates, and when researchers are told to stop looking, that's not just science, that's containment, and what they're trying to contain may be far more complex than a comet. By mid-morning on December 3rd, following the anomalous pulse and the strange behaviour of 3I Atlas, independent observatories, university research departments and amateur astronomers began submitting data inquiries to major space agencies. Something had clearly changed, not just with the object, but with how institutions were responding to it. They weren't responding at all. NASA, ESA and JAXA, all typically active in publishing updates, briefings, or even speculative commentary around notable objects, went completely quiet. No new orbital solutions, no revised magnitude estimates, no thermal emission data, nothing. This wasn't just a coincidence, it was coordinated. Every global agency with observational assets pointed toward 3I Atlas had either gone dark or begun redirecting questions. A generic response began circulating among researchers trying to access scheduled imaging from the James Webb Space Telescope, the Hubble Space Telescope, and the Goldstone Solar System radar. The reply was identical in tone. Observational data for object 3I 2025 Atlas has been temporarily classified under internal review protocols. Access is limited to authorized personnel. Classified, not embargoed, not peer review delayed, classified. This distinction matters. Scientific embargoes are common. They allow research teams to prepare papers or wait for data confirmation. But classification, especially across multiple international agencies, implies a risk far beyond academic competition. It implies either security concerns or the presence of data with implications deemed too disruptive for open release. The silence extended to platforms that normally thrive on visibility. NASA's Eyes on the Solar System app, used by the public and press to track space objects, removed 3I Atlas from its real-time display. ESA's NEOCC tracker suddenly listed the object with an error message. Ephemeris data temporarily unavailable. Even in the scientific journals, submission reviews involving 3I Atlas were paused. In one notable case, a pending paper submitted to the Astrophysical Journal Letters by a team of Swedish and Brazilian researchers was pulled from the preprint server archive just hours after going live. The paper's title, Non-Thermal Magnetic Structure Detected Near Object 3I 2025 Atlas. No reason was given for the takedown. This across-the-board silence was unprecedented for a comet, especially one that had garnered global interest since its interstellar origin was confirmed. Even in the case of Oumuamua in 2017, agencies openly debated its anomalies. But now, with 3I Atlas, even the debate itself had been suppressed. Former NASA mission analysts began speaking off record. One former Deep Space Network engineer told the Atlantic Bureau of Science and Policy, "There's a protocol no one talks about. When a deep space object enters a profile that overlaps with signal intelligence, The science side is told to pause. It's rare, but it exists. Signal intelligence, not astrometry, not cometary science, but communications-related threat protocols. This might explain the parallel silence from SETI Institute, Breakthrough Listen, and the Square Kilometre Array Pathfinder in Australia, all institutions built for signal analysis and deep space listening. Not one had posted updates regarding 3i Atlas since the November 30th report, a paper that noted anomalous repetition in spectral reflections suggestive of internal modulation. In the hours after the pulse, these same organisations went dark. No press releases, no tweets, no media availability, just silence. That silence, in and of itself, became the signal. Because when the most data-hungry institutions on Earth all refuse to comment, and when observational portals begin quietly removing data without explanation, it sends a clear message, not to the public, but to researchers. Stop looking, stop asking, this is not yours anymore. And in that silence, a deeper truth emerged. It wasn't that agencies had no data, it's that the data had moved somewhere else, somewhere above science, somewhere behind protocol. One of the earliest signs that 3i Atlas was behaving unlike any previously recorded interstellar object came from a pattern that seemed, at first, too subtle to matter. Its axis didn't drift. Most comets, asteroids, and even spacecraft in deep space exhibit some degree of rotational variability. This wobble or tumble is natural, triggered by gravitational torque, internal mass shifts, outgassing events, or interactions with solar radiation. Over long periods, even the most stable bodies drift in orientation. But after thousands of images across multiple days and dozens of global observatories, something became undeniable. 3i Atlas was rotating on a single, fixed axis, and had been since its detection. This axis was not random. Researchers from the IAC and the Canary Islands noticed that every high-resolution observation showed the same albedo patching pattern, bright and dark regions used to estimate rotation, repeating with mathematical regularity. When mapped over time, the data pointed to a rotation that was not only fixed in direction, but locked in phase with the Sun's magnetic orientation. This phenomenon, known informally as the fixed axis hypothesis, raised immediate concerns. For an interstellar object travelling at over 60 km per second to maintain a rotational lock over such vast distances and interactions, the internal mass distribution would need to be nearly perfect. But perfect symmetry is not a feature of natural formation, especially for objects assumed to be ancient fragments from distant star systems. Instead, perfect symmetry is a feature of design. Further analysis showed that the object's rotational period, just under 3.21 hours, did not vary even when it passed through regions of solar wind turbulence or plasma shear. Instruments that typically register rotational drift under such conditions, such as ESA's Solar Orbiter and NASA's Parker Solar Probe, detected no deviation in angular momentum. It spun like a gyroscope, silent, precise, unchanging. Why does this matter? Because fixed axis behavior is the foundation for navigation, stabilization, and orientation in spacecraft design. From the Voyager probes to modern CubeSats, maintaining a predictable rotational axis allows onboard systems to track stars, lock onto signals, or adjust propulsion. A tumbling object cannot steer, cannot signal, and cannot sustain precision operations. So when an object from another star system exhibits that same quality, without known thrusters, reaction wheels, or visible stabilization fins, we are forced to ask, what internal mechanisms are holding it steady? Some scientists hypothesized the presence of a ferromagnetic core aligned to interstellar magnetic fields. Others speculated about a form of natural crystallization that resulted in rare symmetrical balance. But these ideas collapsed under modeling. No known combination of material, mass, and spin could explain the resistance to solar torque. One proposal, buried in a now-pulled conference abstract from the University of Vienna, offered a bolder theory, that the object may be using internal gyroscopic dampening, similar to the momentum wheels used in satellites, but powered by an unknown energy source deep inside the structure. That phrase, unknown energy source, was reportedly flagged by European defence researchers, not because it implied a threat, but because it crossed a line The moment a scientific paper uses engineering language to describe a cosmic object, the discussion moves from astronomy to aerospace intelligence. If the axis is fixed by design, then it's not just spinning, it's navigating. And if it's navigating, it's oriented, locked not just to the sun, but to us, to Earth. One final data point came from Japan's Hinode satellite, which captured a unique solar-aligned silhouette of 3I Atlas. In every frame, the object's long axis remained parallel to the solar ecliptic, as if its orientation was dictated not by physics, but by intention. So we're left with this: a cosmic body that does not wobble, does not drift, does not change. A comet, or what we thought was a comet, that spins like a satellite. But with no visible system to explain it. Because maybe we were never meant to see it rotate. We were only meant to see it exactly like this. At first glance, the December 3rd emission from 3I Atlas was mistaken by many for a solar flare response, a common photometric spike that occurs when volatile materials within a comet heat rapidly and eject gas or dust. Telescopes in Chile, Hawaii, and La Palma all recorded a brief brightening event near the nucleus of the object at precisely Borfria 4:12 UTC. The initial reports labelled it a flare. But within hours, deeper analysis exposed something strange. This wasn't a flare. It was a pulse. The distinction is critical. A flare is chaotic. It spreads in multiple directions, lasts several minutes, and is driven by heat and material outflow. A pulse, on the other hand, is highly structured, usually brief, directional, and often non-thermal. What 3I Atlas released on the morning of December 3rd had the signature of the latter. The shape of the event was the first giveaway. High-speed imaging from the Gran Telescopio Canarias showed the emission did not radiate outward in a spherical burst. Instead, it followed a linear path, confined to an axis already observed to align with the object's fixed rotational orientation. There was no expansion of the coma, no debris field, just a single directed flash, lasting 0.87 seconds, before vanishing entirely. Then came the spectral data. Across 6 observational platforms, including data from JWST, Parker Solar Probe, and 2 amateur-run spectroscopes in Australia and South Africa, the pulse exhibited an emission curve unlike anything associated with ice sublimation or impact. There were no elevated hydrogen lines, no carbon spikes, no increase in infrared signature. Instead, the spectrum featured a narrowband burst in the extreme ultraviolet range, with a brief resonance at 17.4 nanometers, a frequency commonly used in plasma diagnostics and high-resolution atmospheric sounding. In short, it looked engineered. But the most unsettling aspect wasn't the content of the signal, it was the delay in its propagation. Ground-based radio observatories in Italy and California both detected a faint electromagnetic disturbance arriving 1.2 seconds after the visual pulse. This kind of offset suggests something highly structured, a light-speed event followed by a slower, mass-bearing emission, a signature separation often used in controlled signaling protocols to distinguish message from noise. What natural comet emits a pulse with an intentional signature lag? To answer that, scientists turned to control experiments. By comparing the event with known cometary outbursts, e.g. 17P Holmes in 2007 and 46P Virtanen in 2018, it became clear that no prior event in recorded cometary history matched the clean structure, spectral clarity, and temporal precision of the 3I Atlas pulse. Those historical events were messy, debris-filled, and driven by volatile materials. This was not. It didn't just behave differently, it violated the known thermodynamic templates of natural flaring. A growing number of researchers began privately referring to it as a non-thermal emission event, a term usually reserved for solar radio bursts, magnetar emissions, or artificial plasma discharges in laboratory settings. One astrophysicist from the University of Oslo under anonymity described it as an intelligent burst masquerading as a cometary anomaly. Further complicating things, the Goldstone Deep Space Communications Complex in California, which monitors radar reflections from deep space bodies, reported no backscatter change after the pulse. If material had been ejected, some of it should have shown up in radar echo, but there was none. Nothing left, nothing thrown, nothing decaying, and yet something was released. So what was it? The best working hypothesis is that we didn't witness an expulsion, but a broadcast, a precisely aimed, timed, and contained pulse, not a chaotic flare. One calibrated to be noticed, but not explained. And its structure, linear, spectral, delayed, mirrors the kind of emission an advanced probe might use to test local signal environments or trigger a reaction from nearby observers, because if it was a pulse, then someone or something might be waiting to hear what echoes back. Every comet or interstellar object that enters the solar system is, by nature, at the mercy of the Sun. Its heat, radiation, magnetic fields, and solar wind shape and sculpt everything from trajectory to physical structure. That's why scientists have long studied the correlation between solar events, like flares, coronal mass ejections, and solar wind spikes, and sudden changes in comet behaviour. But on December 3rd, when 3I Atlas emitted its now infamous pulse, something didn't add up. There was no matching solar event. Solar observatories across the globe, NASA's Solar Dynamics Observatory, SDO, the European Space Agency's SOHO probe, and Japan's high-node spacecraft, reported no flares, no sunspots, no coronal activity, and no wavefronts that could account for the object's behaviour. The solar wind had been calm for nearly 36 hours. The heliospheric current sheet remained stable. The Sun was, for all measurable purposes, quiet. This created a significant problem, because natural cometary flares, dust outbursts, or plasma releases are almost always triggered by external heating events. In particular, when solar radiation spikes, or the comet's rotation exposes a new patch of volatile ice, it reacts, sometimes violently, but always with a detectable cause. In this case, the cause was missing. The team at the Mauna Loa Solar Observatory in Hawaii released a time-synced heliographic overlay from 03 Zeln to 06 Lal TC on December 3rd. They found 0 spikes in X-ray or extreme ultraviolet activity on the Sun's surface. Even the flare index, a metric used to predict the likelihood of solar-driven space weather, remained at category 0. That's not just rare, it's virtually unheard of. Then came the cross-comparison. Analysts from the Heliophysics and Space Weather Division at NASA performed a retrograde timeline match between the pulse and every tracked solar event within a 90-minute observational window. This included not only visible flares and prominences, but also indirect indicators, like changes in the interplanetary magnetic field and solar proton flux levels. None aligned. There were no particle emissions, no shock waves, and no energetic triggers that could have reached 3I Atlas within the window needed to explain its emission. So if the Sun didn't do it, what did? This question pushed researchers into more uncomfortable territory. The possibility that 3I Atlas's behaviour was self-initiated, that the pulse was not a reaction, but an action, a choice. Astrophysicist Dr. Miguel Santoro, who leads heliophysical analysis at ESA's ESTEC facility, was quoted in a closed briefing document. "We have never observed a deep space object behave this way without solar correlation. For there to be an emission of this type without a solar precursor suggests the energy came from within the object, either through stored internal energy or a reactive, possibly engineered process." This statement was not made public. In parallel, several solar physicists began quietly asking whether the pulse was part of a decoupled behavioral signature, one not bound to the laws of thermodynamic volatility, but instead to timing, positioning, or even line-of-sight logic. In other words, was the pulse triggered deliberately when Earth, or another observing body, was in optimal alignment to detect it? The solar orbiter, positioned nearly perpendicular to Earth's heliocentric view at the time, also recorded the pulse, but noted that its angle of incidence was strangely constrained. It was as if the emission had been beamed, not radiated, meant to reach a specific location at a specific time, and that location was us. The absence of a solar trigger doesn't just challenge physics, it challenges intent. Because if this wasn't nature, then we're left with only one remaining possibility: initiation. Which forces us to confront a deeper question. Was 3I Atlas waiting for something, or was it testing the silence? Because in a universe where most things scream with heat and chaos, this one whispered, and we heard it.